today I want to focus on design patterns and what it means for us. I want to start with a little question. What do you expect from today? It's a free-form discussion. Just raise your hand and tell me what you expect to get out of today's class. Okay, as most of you are new, you should know that this setup is an interactive setup. It's not me who's doing the talking all the time. You have to contribute, otherwise it's not as fun. Please.
So far I haven't been working with JavaScript and frontend and backend. So I'd like to see how the JavaScript is used in a field project, kind of.
Okay.
And to get an idea how I can implement on my own knowledge. So I know how JavaScript more or less works, but I don't know how can I put them together. That's what I expect.
From the course or from this specific class? Okay. More about this specific class, design patterns. You have to know why you're here, right? You have to have some expectations.
I think we're going to practice some design patterns. In the beginning, of course, we will need to learn something else, so what kind of types of design patterns we have, and then we would like to try something.
Okay.
And to understand why you need to use it.
Cool, please.
I mean, I did not attend to the beginner's course. I did experience with regard to JavaScript.
Yeah.
I think the focus could be today to focus on how, what kind of code to combine in one module, how to split code up, and what to set design patterns. So there's some kind of best practices using JavaScript.
Yeah.
That would be something that I expect.
Okay. Anyone else? Do you accept that you're clueless about the content? That shouldn't be the case, right? I'm sure that's not the case. I know that's not the case. So please speak up. Please?
Yeah, I've never heard of design patterns for JavaScript, so I work in Java, and it's like there's so many design patterns to solve different problems. So
Yeah.
I'm really interested to see what patterns I can implement at work for specific problems.
Perfect. Hello.
I'm sorry.
One last person, please.
I thought we were going to learn more general pattern, not necessarily related to JavaScript.
Okay, that's good. But most of these people were from the previous class, so I want some new faces. Speak up, please. It's all right. There is no right or wrong answer. Nobody will judge you for your answers. I also don't know what to expect from this class, so it's also okay. But even for that, please raise your hand, some of the new people. Yeah?
Pattern also reminds me of what you can do with processing JS, which is like shape some stuff, like things like that, like take some small drawings that you can put them later on the code and so on.
Yeah.
That's what the type of.
Okay, great. I guess we can start with the introduction. Some little boring bits about me. Oh, sorry, please. Yes, I'm recording it. I hope I am. Yeah, looks like I am, but no promises. At least this time we have a presentation that you can go over. All right, a little bit about me. I work here in a company called Uml GmbH. We're building electric scooters, if you've seen any around the city. So they're like Vespa, but with electric batteries. And I'm basically leading the software engineering department there. I'm also, I would like to call myself a founder of an organization called Lonca, which means guild. It's a software craftsmanship school for women. We have several students who are training to be software craftsmen, which is a whole branch of software development. It's nothing technical. It is a philosophical thing. It basically treats software engineering as a craft, like carpentry. And yeah, basically we train people to be better software engineers. I am pretty much active in open source communities. I have a lot of libraries, open source libraries and projects that you can go through. If you're looking for code examples, 90% of it is in JavaScript. So if you're looking for some examples that you can learn from. You can definitely go into my repositories. I have stuff that let you develop hybrid mobile applications, microservices, brain signal processing, audio processing, and a bunch of other stuff. So that's briefly about me. And yeah, basically I'm also teaching JavaScript at Women TechMakers Berlin, as you may have already seen. So as you would remember from last year, I like to tackle technical issues in a different manner. The goal is definitely to build software, but we have to understand what we're building. We have to understand why we're building it, or why we're doing something in a specific way. And it's also true for design patterns. So this is an architectural topic, and this is an architectural class, which means you won't be writing any code. I will show some code to you to explain them, but this is mostly philosophical. So this is why we wanted to kick off this series, advanced series, with this topic, because it actually forces you to think about your design, about your code, about how you would approach this problem. And what is the problem? The problem is not to develop an application. Definitely not. The problem is not to ship some value. They all come one way or another. The problem is, how do you make sure you deliver this in the least disturbing way possible for your colleagues? Because your friends are working on the same project with you, your colleagues, right? You are part of a certain team. Every code you write, every single line you write has the potential to annoy them. There's a metric called what the fucks per minute when doing code reviews. So when somebody is looking at your code, your proposed change, the quality of the code can be measured in number of what the fucks per minute they say while reading your code. Because let's admit it, when you're going through your colleague's code, it's like, who wrote this? You know, like, this is an abomination. This shouldn't have happened. Nobody likes another person's code most of the time. We even don't like our code from 6 months ago. So, you know, the code that we ourselves wrote. When there's a bug, we tend to say, that was not me, I didn't do it, that's this guy. And we kind of try to blame people around us because it's painful. Writing code is painful, right? So the whole idea is about human psychology. And design patterns is a way to lower this complexity and remove the friction in delivering value. So the problem, again, is how easy it is for you to write code, or how easy it is for you to understand code another person wrote. Anybody doing maintenance at their work? Like bug fixing and stuff? Yeah, 1, 2, 3. You can admit it. I'm also one of those guys. Hello. It's nothing to be ashamed of. But it's hard. It's hard because you're dealing with the past. And as in personal past, it's always hard when, you know, the past haunts you like a ghost, comes to get you. The moral of the story is we write code for humans to understand. It's not about machines. Machines understand huge different set of instructions, as we call them, like machine code, ones and zeros. That's what they understand. If our goal was to interact with the machines, we could write in ones and zeros. But we first invented something called an assembly, a very basic language. And then we went on to invent Lisp or C or C++ and Java and now JavaScript. And we're going forward with higher and higher levels of languages. Why do we do this? We do this because it's horribly painful to write code the previous way, like ones and zeros. Machines can understand everything. Actually, they are better at understanding those. If we could write ones and zeros all our lives, we would have amazing performance in our applications. But we can't do that because we're limited, we're human. And the idea is basically the code that we write every day, it's for humans to consume. And that's why you have to take extreme care in every single line that you develop. And design patterns is basically a way to help you, a let's say, a guide to walk you through, because it's a lot easier when you have a shared language. But I guess I made it clear, this is a very, very complicated topic. It has no right answers, it has no wrong answers, again, like everything. It has some best practices, but those best practices change depending on the language. They change depending on the environment, depending on the teams that you're in, depending on the era that you're in. Like in the 90s, there were some patterns that were really great, but in 2018, we don't need them anymore. So it's extremely complicated, and the biggest reason it's complicated is it directly deals with human psychology. So you have to keep this in mind throughout this lecture. So, a little bit more background. Are you bored yet? Is it interesting?
Of course.
Okay, thank you. A little bit more background. Again, it's really hard to write software. Why don't we write ones and zeros? Because that is the best thing machines understand. If we were talking to machines, why don't we write ones and zeros all the time? Because basically you can't. It has a very, very high tax in your brain. You have to remember, how to do a for loop with only 2 digits, ones and zeros. It's doable. You have to memorize some patterns, or you have to look them up all the time. It's a very high tax. And we are trying to solve this complexity. That's why we have a lot of high-level languages and frameworks like front-end frameworks and back-end frameworks. They're supposed to ease this pain, right? But they don't. And that is also another big problem. Why don't they do it? They are doing their job properly. They work the way that they're set up. The problem, again, the bug is we are using them. Who is using some sort of a framework, whether it's a CSS, JavaScript framework, a backend or a front-end framework? Like almost everybody, right? How do you make sure you use it as it's designed? Can you ever make sure that you can use a framework the way it's designed? You can't, because the author, the person who created that framework, they also don't know all the use cases. You may have a very legit use case in real life, but hello, welcome. But the author of that library, of that framework, they're also human, like you. They can't know, predict, and work for everything. So the thing is, we are complicating stuff. Every single line that we write is complicating the lives of our colleagues. And this is a fight that we can't win. Because the more code we write, the more value we ship, the more features we ship for the business, and the more money we can make off of it. But it's also killing us. So what is the job of a software developer then? Again, it's not to deliver code, it's not to deliver products, it's to solve a certain complexity. Selling some stuff online in an e-commerce shop, that's a complexity. You have some products, you have some customers, they want to buy those. It's a complexity, it's a problem. And you basically try to solve it by writing code. Which means, if you solve this, you'll write maybe 50,000 lines of code. It's basically a burden in your colleague. So you have to live with it all the time. The code complexity that's growing with the lines of code you write. But there's another metric. How do you make sure that the software is easy to maintain, a joy to work with? Did you have any experience with with a beautiful code base? You love to work with it. Every day you look at the code, you love it. Like, that's perfect. Anybody? 1. You're very lucky. 2.
Because I start every day again.
Sorry? Because?
Because I start every day.
Okay. Yeah. So the thing is, actually there is research about this. The code complexity grows exponentially. You write 10,000 lines of code, the complexity grows by 1 million. You write more, it's 1 billion. So whatever you do, all the frameworks that you use, you don't use them to get stuff faster. You use them so that you don't have to write that yourself, so that that complexity is solved for you, so that the more lines that you write, the complexity doesn't grow, but stays constant. So the idea is whatever you do, whatever modules you do, you develop, you add, the complexity remains constant, or at least linear. Like anything except exponential is great. Anything below exponential is great. Remember from the first part, we developed an API on the backend, right? We had some classes, some database collections. We were writing stuff through an API to a database. So that was a complexity on its own. It had a certain mechanism, right? And you went on with your projects and did 5 times of that work. Was it more complex? There were more lines involved, yes, but it wasn't more complex because you were repeating the stuff that you did before, right? You had an entity, you had a model, a schema, a database schema, and you had another one, and you just had another one. And you wrote the APIs to create records, to read records, to update records, delete them, or link them together. So there were nothing new actually. Wherever you look, you saw the same similar structures. So this is what we mean when we say keeping the complexity low. You can repeat stuff, certain workflows, but the number of surprises is basically gives you the complexity. If you look at something and you don't understand at first sight what it means or what it does, a certain piece of code, then that's complex. But if you see pages and pages of code and you instantly identify, hey, this is doing this thing, or I see these constructs, how these things are connected together. If you can identify certain repeating patterns, then that's not complex. Then that's actually very easy to understand and to map. So basically, this is the secret that people are lacking in software engineering. That's why most people hate their jobs. That's why they change jobs every year, because they can't stand the complexity anymore of their old code base. That's why they hate their code from 6 months ago, from a year ago, because it's a horrible, horrible mess, and they always blame the next developer who made maintenance changes and bug fixes to their code. But the idea is to be very intelligent with code design. You're not asked to write lines of code. You're asked to deliver solutions that are maintainable, that saves the future instead of complicating it. So you should keep, again, you should keep this in mind when writing code. And again, design patterns will help us by showing these constructs, like these are the set of rules that you can make use of, so that it's very easy to identify. And it's like a Lego block. So you bring them together and then they do a very complex thing, which would otherwise require a huge amount of time and effort if you did it without certain repeating constructs. So, I don't know, think about the wall, for example. There, it's made of bricks, right? Does it have any complexity? Not really. You just have a pile of bricks, you pile them up, and it becomes a wall. What if some part of it were, I don't know, a heater? Like you wanted to make a wall from a heater and bricks and some chairs and desks. That wouldn't really work. I mean, you could maybe use the desk plates as a panel. I don't know. That would be very complex. So the idea is find a construct that works for you, like a brick. It's a very simple construct, but you can build anything out of it. You can build huge buildings, you can build walls inside the buildings, you can kill people with it. That's very handy. So it's a multi-talented tool, and you should find stuff like these that works for you. So, does anybody know signature stamps? So it's like an address, or people get their signatures on the stamp. Why do they do it? Because they're bored of signing stuff all day long, and they want to scale this business out. Like if you can get 10 of those, you can give them to 10 people and they can sign stuff for you. If you are running a government organization, that's very handy to have, because you cannot be expected to hand sign everything. That just doesn't work. So we come upon these constructs everywhere in our lives. Like we have paper money, right? We have bills for 20 euros, 50 euros, 100 euros. We don't have 120 euros, or we don't have a 170 euro bill. We don't have custom constructs, right? We have some bare-bone building blocks, like coins, and we use them together to make up any amount that we want, right? These are also patterns that you're using in your life. And the idea is, it's very easy to identify. Like everybody knows when they see a 100 euro bill. Everybody knows when they see a 5 euro bill. And you can tell the difference very, very easily at first sight. Like there's no complexity at all, right? If I present you two different bills of money, you can tell which one is which and what you can buy with it. It's very straightforward. So the code that you write should also be this straightforward. And again, it's what design patterns are about. There is a certain very controversial topic about machine learning. Anybody read anything about machine learning? You know, do you follow the news? Kind of AI, machine learning stuff. Who thinks machines can be intelligent? Raise your hands if you think machines can be intelligent. Come on, you're lying. Huh?
It depends how you define intelligence.
Yes, how do you define intelligence? Stephen Hawking has a quote on that, on intelligence. He defines intelligence as the ability to adapt to change. So that's an amazing description in like 4 words, the ability to adapt to change. It's an amazing description. Think about machines. Machines are trained to discover certain patterns. You give them a picture of a tree, it understands that's a tree. You give it a picture of a car, it learns the details of a car, and now it can tell whether the next picture that you give it is a tree or a car. But if you give it a picture of a cat, it doesn't know what to do with it because it's not trained on it yet. So the picture of a cat is a change in this case. And humans are easily adapting to change. When you see a picture of a cat, you know what it is, right? That's a picture of a cat. Or if you see a picture of a creature that you don't know, you can at least say, it looks like this. Now machines can't do that. They can actually never be intelligent. They can only identify the patterns that you show them, that you give them. And they can fuse patterns to increase their understanding. But whenever they are presented with a change, you know, something they were not trained on, something they did not expect, they fail. This is why humans are intelligent and machines are not. But this doesn't mean that they are bad at machine learning or identifying patterns and stuff. They are very, very good and fast at identifying patterns. Because it's like monkey work. When you have a certain pattern, when you can make out the rules of a certain pattern, everybody can understand it, you know, with the blink of an eye. And machines are basically trained for this, and therefore they excel at this thing. Which brings me to the next topic, again about design patterns. If you remember the original discussion, the background, it's software development has a very high tax, a very high cognitive load in your brain, right? And we're trying to solve that complexity. If you can identify everything at first sight, then there is no complexity, then there is more room for your creativity and for your intelligence to shine. So that's why we have to use patterns, because once you identify a pattern, it's done. You can build anything with that. So anybody here could bring together different amounts of paper bills for, I don't know, 400,764 euros, right? You can do that easily without even thinking about it. So the idea is when you solve the complexity of the building blocks, you can build software a lot faster. And now let's look at some software principles. Before we start with design patterns, there are some stuff that you need to learn, which we will not talk much about today, but these are reading material for you. Anybody who knows what KISS is? Keep it simple, stupid. Okay. The idea is whatever you do, whatever you write, don't overcomplicate it. Especially engineers who are junior to mid-level, they like to show their capabilities by writing more complex code, but that's not useful for anybody. You have to keep it very dummy, very dumb, so that the next guy who comes in to maintain your code can actually understand it. It's okay if it's stupid. The second one is the dry principle. Do not repeat yourself. Anybody who knows this from their professional life? Okay. The do not repeat yourself thing is pretty obvious. If you have some patterns, they are automatically available for you. If you have some building blocks, they are automatically available for you to reuse. So if you find yourself copying and pasting the same code into multiple places, if it's 3 times, 4 times, 5 times, you are actually repeating yourself. That's you are carrying over, copying and pasting and multiplicating that complexity. What you have to do is to abstract away this thing in a single building block, so that it's maybe a single line of code that you execute, a function call that hides away this complexity, so that you can have certain complexity in a single place and call it from multiple places. Instead of copying it over and over again, you basically centralize the complexity. It's like Ghostbusters. Like there are ghosts around and you have to trap them in a single thing, and you put them in a vault, which is a lot easier to maintain, and it's a lot healthier for the city, right? The next thing is solid principles. Raise your hands if you heard of these before. Perfect. Raise your hand if you know these by heart. Okay. So this is the core of design patterns. Actually, most of the design patterns are coming from these principles. They are built upon these principles. So solid principles, I will briefly mention them because they are very, very important. They will basically save your life as a software engineer. I cannot overstate how important solid principles are. And it's like a collection of 5 different principles. And we like puns, so people call it solid because it's really solid. It's really nice. The first one is single responsibility. Any block of code you write should be responsible for doing one thing, and they should be responsible towards one other entity. So the idea is, again, the code that you write, that's growing, right? By the day, you write more and more code into that. Like in the first class, we had a person class that were making friends with someone else, right? Now that's a very good example. Person class is a very simple class that you can build anything about a human, right? What happens if they need to run a government? What happens if they need to form a political party? What happens if they need to get a job, become doctors and stuff? What happens if they have to report to both to their managers and to the tax authorities, for example? Like these are different responsibilities, and as humans we can do that because we are good, very intelligent creatures, but our code is not. So the idea is whatever code you write, it should be reporting to one single entity. So if you have tax liabilities and if you have your work that you have to go to, these are different responsibilities. They don't go under a single class. This is basically, it feels like a no-brainer, right? You know, why should it happen in a single class? But it does happen. This is about solving complexity again. You shouldn't give more responsibility to a class that it can take, that it has in the first place. It's okay to have more and more code constructs collaborating together, but it's not okay to give more responsibility to a single unit. You cannot expect a person to fly like a bird. That's a different thing. Or flying in a plane. That's a very good example, actually. You are a person flying to another country in a plane. Are you actually flying yourself? No, right? The fly method of a person wouldn't exist, therefore, because you're not flying on your own. You're flying in a plane. So that's actually the plane's responsibility to fly you over, although you are going from one place to the other. So it's a very simple construct, but very hard to get. And you'll be amazed when you look into your code to identify the number of responsibilities in a certain code block, whether it's a class, whether it's a function or a component. It's very important. The next one is open-close principle. The idea is your code, anything you write will change, right? Because we need to ship more features. We want to use more and more code and deliver more value. The idea is, again, whether it's a class or a package or a component, it should be open for extension, which means you can add new capabilities to it. But it should be closed for modification, which means the previous features added to it shouldn't be modified. Like if a person was flying before, like a Superman, then you don't expect them to lose their flying abilities during the course of time, during the lifetime of your software. You shouldn't modify their internal structures, internal health. Like people get old, they die, that's true, but code doesn't do that. So if you have, you know, a very capable class and then you modify it and remove some blocks and, I don't know, you're doing a refactor or anything, that's a different case, but you're changing its previous behavior. It breaks your colleague's code. It's very simple. It breaks people's understanding of that construct because the previous time they looked into that thing, they knew they saw a different set of functionality. So anything you do, you can grow, you can add new functions, you can add new methods to classes, that's all right. But you shouldn't modify past behavior. The past is past, we're okay with it. Whatever mistakes we did, that's all right, that will stay. The next one is Liskov substitution principle. This is a that's an amazing woman, Barbara Liskov. You should read her papers on computer science. That's an amazing, amazing personality. And it's very hard to grasp even for the most senior engineers. This is basically where everybody fails. Liskov substitution principle states that a derivative class is still the or can still show the features and the actions of the parent class. So you have an animal and you have a bear or a shark. They are both animals, right? Whatever you have in the animal class as a feature, you have to have in the shark class. But this is very annoying. Like, think about the number of legs. Would you put that in the animal class or the bear class? A snake doesn't have legs. A fish doesn't have legs, but they're animals, right? So they have to pass as an animal. Wherever an animal is accepted, a snake should fit. That's a lot easy in biology. We classify things. We say that these are both animals, but in code it's actually very hard because you have to show that complexity somewhere. Something should have legs, and again, you don't repeat yourself, right? So humans have legs and birds have legs. it should be in a single place. It should be implemented in a single place. So you cannot have a different set of walking mechanism for humans and for birds, even though it's a little bit different. The thing is still walking with legs, right? And we have two legs. And where do you show this complexity? Both are animals. A snake is also an animal, again. It's very hard. It's very hard to maintain this notion, because as you specialize in child classes, like there is a shark, like as a general class, there are some killer sharks that want to kill people. And there are some normal sharks that you can pet when you dive, right? So these are specialized smaller subclasses, child classes of the main shark class. And where do you put biting? So where does that complexity go? The nice shark doesn't bite. The other one bites to kill. They both have teeth. So teeth should probably go to the parent class, right? The idea is you have to build your software in such a way that you can still identify and use either of the sharks as a shark class, whether they're killing people or they're not. If you want a tank full of sharks, it shouldn't matter which version you get. Although if you're human, it could matter, but in the end, it shouldn't. If you want a forest full of birds, it shouldn't matter which type of bird you get. If you identify the birds as chirping, right? But if I tell you that there are some birds that don't have any voice, what do? That's not a bird anymore, depending on your description, because you said birds chirp. Well, this one doesn't. Or this one doesn't fly. Chicken is a bird. It doesn't fly. So birds actually can't fly in your code, right? Otherwise, you're breaking this principle. The chicken doesn't pass as a bird. If your bird is supposed to fly and the chicken is a bird but it doesn't fly, this thing won't work. So it's very, very complicated. You have to read it for yourself and you have to see examples and understand the Liskov principle. But when you solve this, you solve a huge, huge amount of complexity in your code. When you internalize this and base your software designs on Liskov substitution principle, your colleagues will love you. It will be a lot better. The other topic basically derives from Liskov substitution principle. It is built to solve this flying or non-flying bird problem, right? So this is a real use case. Like you have a bird that is supposed to fly, but chickens don't fly. What do? You don't put that flying functionality in the bird. You create something called an interface, like a contract, that defines the ability of flying, okay? It says, hey, here's a contract, and here are the terms to call something that can fly. Like, if anything can pass these 10 points, you can tell that they are able to fly. This could be a bird, this could be a human, anything. I don't know, how do you define flying? Like being in the air for more than 10 seconds? Or controlling your altitude in the air? What is the definition of flying? I don't know. But you define it and you put it in a contract. It's called an interface. Okay, it's a very small interface. It just defines things that can fly. Now, this is a very important point. Remember about single responsibility and derive principle. You are not supposed to repeat yourself, right? You could identify one certain interface that guarantees you that anything that has that interface, that has that contract, can fly. So you don't have to look for a specific ability anymore. You don't have to see if it's a bird but not a chicken, or if it's a human but also Superman. You just look for the contract. You ask anything that comes your way, a class, an instance, hey, do you have the fly contract? And if they say, yes, I do, here, I have a fly contract, then you don't care anymore because all you want are flying objects. So you contain the complexity of flying in a single thing, in a single contract. And what do you do then? The birds that can fly, they say, okay, I can get that contract because, you know, I can keep in the air, I can move to distances, and I can control my altitude. Then they are basically satisfying that contract. So that's good. They are birds that can fly. The chicken says, I don't know that. I can't do that. So I can't fly. I don't have that contract. It's okay. They are still birds. Now you remove the complexity and responsibility from the bird class and made it something generic that you can reuse for humans as well that are flight capable. Again, this has to be a native feature, so I'm always talking about Superman because that's the only guy that's flying. I don't know if we would qualify Batman as flying. But the idea is, with interface segregation, you have a lot of interfaces. And every tiny feature that you want to identify, but it's very hard to put in a parent class, like the bird cannot have the fly method, or the shark cannot have the bite method because some sharks don't bite, or a person can't have the work method because everybody works, right? So these are all interfaces. These are all contracts that identify certain behaviors and that contain certain behaviors. And they are shared by different objects. Interface segregation tells you to keep your classes very light. So you don't put a lot of functions into making classes, you know, huge, like 100 functions or anything. But it says use interfaces and implement those interfaces in specific instances, because the parent classes, you know, you don't know how you will extend them into new classes down the road. In 6 months' time, you don't know if you will have a hybrid dog or a hybrid shark that can do this or that. So don't bet on it. Don't bet on the bite method being on the shark, because you may have a very unique shark that has no mouth. So the idea is everything is a collection of interfaces. Like, let's talk about a car. What interfaces could you identify in a car? What is a native property of a car? And what is not a native property of a car that can go into an interface? This is opinion time.
So we can move on the street or on the ground?
The ground. What about hover cars? Or cars that can also go on the water? Anything else? What can a car do?
I just have a question. How to decide, or how do you decide if you need to have a separate interface or if you put it in the.
So the endpoint that will come, this is a spoiler and I love spoilers, the endpoint is you don't. Everything is an interface. Everything has to have an interface. We're just lazy people who are not using interfaces and hard coding everything into our classes. That's why we suffer so much. But every single functionality should have an interface. It can be a shared interface, like flying can have multiple methods, or swimming also can have a diving method, for example. But it doesn't mean that you should have concrete implementations in functions in certain classes without interfaces. Because that is a piece of code that you cannot reuse. That's a piece of complexity that you cannot reuse. We were talking about cars. Give me something that a car should do natively. Does a car have windows?
Transport people.
Transport people. That's good. Yeah, a car should do that, right? Maybe.
You could just transport objects.
Objects. Yeah.
So that's the possibility to move from one point to another.
How do you define moving? Like any kind of movement? What?
Accelerating and decelerating.
Oh, that's great. What if they keep at a certain pace? Like,
Then acceleration 0, I don't know.
okay.
But that's also potentially to acceleration of the movement because
It's a running wagon that you have to jump. But the example was good. It can transport people, and the counterexample was, well, it can transport objects. What we get here is we are generalizing stuff, right? So that's what concrete classes can do. They can work on generalized concepts. You shouldn't say that a car can transport objects. You can't say that a car has a driver. There are autonomous vehicles. You cannot say a car has 4 seats. There are, one-person cars. A car may not have a cargo, so it may not even be able to transport most objects. But the idea is you're working on very broad, generic ideas and ideals. And this is what concrete classes can do. You can expect a car to be able to transport an object. And you don't define what that object is. But anybody that has an interface of an object that identifies as an object is then it's okay to transport by a car. So if a person is an object, which they are, right, then a car can carry a person. If a cat is an object, yes, they can carry a person. So concrete classes are great for this general pattern, and individual implementations are to be made over interfaces. You have to have this object interface, and certain things will implement that object interface. You were saying something.
Yeah, I have a question. It seems like whatever characteristic you find to define a car, you could potentially find an example where that's not true.
Exactly.
But what if you kind of define the car as possessing at least one of these qualities? Like either it can transport something, or it can go from one place to another. And I was just wondering, is there an equivalent to that in any way?
Well, the thing is, we're doing it all the time. Like nobody is using interfaces. Have you seen any interface in your work? Yeah, a few of you. Who is using interfaces daily? Daily. Perfect. And I'm talking about the class interfaces, right? Not the user interfaces. Okay, what about you? Okay.
Yeah, but I think it depends on the language because, for example, in Java, interfaces are quite a good thing to do because it's very easy to structure code and to permit or disallow using one method. While JavaScript is more like do whatever you want.
So is that the case? Why do we abuse the language? Like, good software design it has no relationship to any language. You can do good software design in any language. And these are basically solid principles. They are not for a single language. They are principles for software engineering in general. And they apply to JavaScript as well. You should be using interfaces in your JavaScript logic code, but you're not doing it. And that is why our code sucks. The principles are there. It's clearly defined, but we're not doing it. We are hard coding features into classes because we say, okay, I saved the date and I don't care what will happen down the road. That's why we have to refactor the classes all the time. That's why we have to modify the behavior, because you first start out by saying that a car has a driver and has 4 passengers, and then there are bigger cars that are autonomous, and you have to change the behavior of your code. What happened? You just violated open-close principle. You modified your past behavior. You now say a car doesn't have to have a driver. Your previous code broke. So everything is connected, and you have to watch out for these things. It's very, very hard to get solid principles right. The last one is, again, very weird, hard to explain. It's called dependency inversion, or inversion of control. And one way we do that is by utilizing something called dependency injection. Anybody heard dependency injection before? Okay. So that's one way of doing dependency inversion. Can anybody tell me a few words about what inversion means there? like if you have any experience with dependency inversion or dependency injection. Why do you do injection at all? Why is the pattern?
I mean, without inversion, you're having a class and you're telling in your code what kind of object you need in order to make this class function. So it's doing instantiation by using keyword new. And when you use dependency injections, more like you configure in a centralized place what kind of object this class is going to need, but you don't have to bother with it in your class itself. More like this.
Yeah. So the idea with dependency injection is certain classes depend on certain classes to function, right? For example, a car currently requires a driver to be able to move because we currently don't have autonomous vehicles yet. So the driver is another class, a car is another class, but the driver is an entity on its own. The car doesn't create its driver, right? Did you see any car that can give birth to a person and make it drive? No. So the car doesn't instantiate the driver. So you will never see a code in the car as new driver. The driver always enters the car from outside, right? They always open the door, go in, close the door, and start driving. The driver is a separate thing that's living on its own. It's a different entity. So the idea is, although the car is depending on the driver is coming from the outside. It's injected into the car. And in terms of code, you would see, accept driver as a method, for example, for the car. A car could accept a driver that can take a parameter of a driver from the outside. And, you could have a driver that you instantiated 30 years ago, a person of 30 years of age. You can pass it to a car as a driver and it would work. But again, the car doesn't control the creation of the driver.
So that means driver can be a software.
Yeah. That's a very good point. Can it? The driver, what usually people would do is the driver is a concrete class. Like it's a class that you can instantiate, that you can use, right? Which means the car actually depends on the driver. If you change the driver, the car has to change because maybe it will lose its driving abilities. Do you see where I'm coming at? Maybe it could lose its driving abilities. Abilities were defined in behavior, were defined in interfaces, right? Now, keep in mind that everybody is violating open-close principle. You will see that people will mess with the driver class, will make sure it loses its driving ability. So, can you actually trust the driver class to be able to drive a car? What if some person just goes in and changes that class and removes that drivability? It's still a driver. It's like you can forget how to drive. You can lose your hands, feet, whatever, so that you cannot drive anymore. But you're a driver, you have a license. This is very tricky. You have a license. Technically, you have a contract. But you have to update it, of course. But the idea is, a car cannot rely on a concrete driver class because it may change, it may break. Dependency inversion then comes into play. That's why it's different than dependency injection. Dependency injection is one method of doing it. But the idea is a car should depend on something that can drive. So, driver interface that has a method called drive, for example. A car should define its own dependency. A car should say, I have these functions, okay? If you can do this and that, then you can drive me. So a car is in charge of its dependencies, all right? It shouldn't depend on a driver class that is defined somewhere else in the code, 40 years ago with some functions. It should create its own set of rules and enforce those set of rules. A car should say, for example, I have a start button, okay? I don't have a key. And then it should say, in order to drive me, you have to be able to click that start button. There's no key to turn. So this could be or could not be in a driver class. A driver can click on a button or cannot click on a button. The car shouldn't depend on this. So the car cannot accept driver as a parameter.
So does it mean then that the class shouldn't depend on another class?
Yes.
Just another class, but the attributes of the class should be checked before it's used.
Exactly. Yes, and that's how you use interfaces, or that's why you use interfaces. So the car class defines an interface. It defines the interface, or whoever writing the car class defines the interface and says, in order to derive this car, you need these and that attributes, and this method and that method that takes this parameter and that parameter. And then, if you want to be a driver for that car, you should be taking that interface and implementing that interface. Okay? So here's a car. Here's a can drive interface, and here's a driver. What happened before was the car would directly depend on the driver that has been defined 20 years ago, just because it can, it has some methods. But the car wasn't in charge of the dependencies. That's why it's called dependency inversion. This is the normal way people do software, and we invert it. Now the car doesn't depend on the driver anymore, but the car depends on a third party called CanDrive. That's an interface. Okay? And the driver now depends on that third party, which is defined by the car. So car defines something and driver depends on it. We inverted the dependency in between car and driver. Previously, car was depending on the driver. Now the driver is depending on something that car created. And what did we gain with this? We made sure nobody can mess with our drive method because we are defining the rules for it. If you want to drive me, you have to comply with these rules. That's all. You have to have these attributes, you have to have these methods, and of course this is not a manual check. This is why you define an interface. You define all the complexity of being able to drive that car in a single place, and whoever has the contract, whoever says, yes, I have it, here's the proof, I am implementing that interface, then they can drive that car. So the dependencies can't change in this case, unless you want as a car, right? Now you don't depend on anything external anymore, but still you can accept a driver to drive you. Isn't that great? Like, you can work with third-party software, but even if they change, you don't care. Because if they lose the contract of can drive, they can't drive anymore, so they will not come to you. You make sure very easily that whatever comes your way can drive you. So this is, again, something that nobody does. It requires use of interfaces. Since nobody is using interfaces, nobody is using dependency inversion. That's why our code is a huge mess that we hate. You were saying something. Yeah, okay. So, solid principles. Even if you don't know any design patterns by heart, even if you don't employ any design patterns, if you can get a hold of these 5 rules and you can employ them in your software, then you'll be good for good. And yeah, basically it looks like 5 letters, but there are hundreds of academic papers on it, how to do them correctly and why we don't do them. There are some psychological papers as well. If you're interested in the topic, you can read. Do you have any questions at this point? Anything? No?
Will we have code examples later to
For solid?
Yeah.
No. This is why this is an architectural topic. I will show some code examples for design patterns because that's a lot easier to identify in code. But these things you have to read a lot. Like, this is basically a university course of 14 weeks and it's a very, very huge topic. So I encourage you to study. And of course, we are there on our Slack channel, and we can always discuss these topics there as well. I want to take a break for like, I don't know, 15 minutes or something, and then we'll get back with the second part of the course. Okay? Hey.
Lisa.
I know.
Just making sure. There is an elevator here.
Okay.
So the guy just has to give the key. So whenever you come, no problem.
Okay. Can we use that while leaving?
Sure.
Okay.
Yeah. We just have to let him know.
All right.
And he said that we should finish between 9:15 and 9:30.
Okay, is 9:30 okay? Like I can do by 9:30.
I know. Just because he's the last one here.
No, it's alright.
Okay. Alright, that's fine. Would you like some water or something?
Yes. Actually, let me try and check what we have.
And refresh my because I had to do some other stuff which was supposed to be like, I don't know, some kind of enterprise create workflows in your company which doesn't have the coding itself. No, I had to do it. Some examples, but they were not very technical. And once they went to have the other class, which was so far it's okay, but I don't know. Let's say for one semester we have like 5 one semester. One or two games, then my whole study was sort of project. And so it's really sucks when I was really and also include 5 people in one project. 5 projects was very works, exercise studies, a lot of different days. So especially when you want to Yes, so I'm still surprised because I expected more of you than facilities I was trying to get. Yes.
We were saying after this, people who have
first class had reserved single segment.
At least everyone, you're right, everyone got in
No. And like, well, we were one flow. It's great. But like, well, you saw it was very I mean, they which I can't. I can just can do it like this because that's how it works. But I don't understand. Maybe what this
small.
Yeah. I mean, it's what I think you are interested in. Because I think she was also teaching. She had this good solution. She needs to have it. Same thing with Python.
That's why you do it.
Just check the whatever. Yeah. I was also like, how am I doing it? Like, how make it spending like 5 years back.
Hello. Hey. I would like to start by asking you what you have, what you remember from the first part of this lecture. Tell me what stood in your mind. What do you remember from the first part?
Solid.
That's good.
Kiss and dry.
Kiss and dry.
Make sure you write understandable and easy code.
Yeah.
Use interfaces.
Use interfaces.
How to simplify writing code to make it not too complex.
Yeah.
So, but right now, answer the question.
I think you said that our code sucks.
Yeah. I mean, there's a problem with you if you don't hate your code in 6 months' time. It means you didn't develop, you didn't improve as a software engineer. There is no end to improvement as engineering goes, so it's just normal to look back and hate the stuff that you wrote. Like, not even, you can even say like, who's the dumb person who wrote this thing? Even though you see your name on the commit, you see your nickname on GitHub, but it's normal. Yeah, you were saying?
Yeah, I remember that storage is very, very important, so go learn more about it.
Yeah, you have to read more about this. This is something, you know, like I would take months to teach you, but it's better you learn on your own and in your own code examples. So please make sure, especially the last 3 items, they are the harder ones, especially you get them right. They're fun reads. So of course, there is a certain thing called the UML, Unified Modeling Language. Anybody experienced with UML? 1, 2, 3, 4. That's good. It's basically a way to document software. And we're using patterns, right? We see some lines of code, we can identify them. But we could use some graphs, some diagrams, some charts, some boxes and lines to document or to identify certain patterns or our application structure. And it's a little bit easier to see the big picture when you look at it. So this is a very simple example UML diagram. You see a car, a driver, a wheel class, and a person class. These are classes denoted by boxes. And you see that the driver drives the car, and the driver has 4 wheels, for example. And this basically gives you a structure of the class interactions. So without looking the code, just by looking at this thing, you understand how many classes you have and how do they interact with each other. This is an example from a very, very complicated version. This is like 1/20th of the graph, but this is more complex. So the typical use case is to identify the properties and the methods in the classes. So you also document them. You give this to a software engineer so they know what to write in that class. They know which properties it should have, which methods it should have. So this is like a class node, a UML script, stack, script composite. The names don't matter. These are just classes. Sometimes you see numbers like this class structure makes use of this package. It can have only one package, but sorry, it can have any number of packages denoted by the asterisk here, but each package can have only one class structure. So it also gives you the mode of operation and the relations. And it says, you know, this package is implementing this script composite. This is actually a pattern, a composed pattern that we'll see today. And it's denoted by this empty arrowhead. So this is a language in and of itself. Every shape has a meaning, but it's a lot easier to read and understand. So I encourage you to study UML diagrams, because then you can identify the patterns much more quicker. Those were the class diagrams, and this is called the sequence diagram. It shows you the flow of software, the flow of logic. So you have some actors, like a user, and they get in touch or interact with some certain classes, like first class, second class, last class. Again, the names don't matter, but they can either call a method and create a run here, and you know, the first class then is calling the second class. It creates a request, makes a request to the second class. Second class makes sure to pipe this do work thing to the last class. So what you end up is your do work ends up in the last class, and then, you know, the flow terminates here because this is done. So it calls the result. The dotted lines ensure the dotted lines means that it's a result, and the straight lines is an execution. So you execute the do work method, you get a work done result, and the second class turns it into a request response, and it's basically sent back to the user. This is a very simple example of sequence diagrams, but these are what we use to document our software, and usually it's also something like this. Like there's some subgroups of actions in sequence diagrams that you can identify, like authorization, token generation, or accessing a resource. And you can have a database or another object, like it doesn't have to be a class all the time. It could be an application. But basically you can see how you should build that software, how you should build that logic. These things are unfortunately underused again in the industry, and this is also again why most of our code sucks, because we don't know the structure. Like, you can only have this in your head, visualize this in your head, but what happens if you have like 20 actors and, you know, this flow is like, currently this is 6 steps, but if it weren't classified, I could show you some sequence diagram that we have at work that has like 100 steps, 120 steps for a single logic. It's almost impossible to keep the whole thing in your mind. It's a lot easier when you have this documented. Whenever you feel lost, or whenever you're teaching a newcomer, you just refer them to this, they look at it, understand it, and then they can operate. They can change. Yeah, please.
I didn't mean to interrupt you, but I was just wondering, at what point do you, I guess it depends on how large the team is making an application on the web, but at what point do you make something like this? Like, do you actually do this before you begin, or do you do this? Yeah.
The truth is, you do this the first time you have an idea to write software in your head. You do this in your head. That is the problem. I want this to be on paper, and most people don't have this on paper. It should come before the actual coding session starts. So before the first line is written, you should have some documents, not everything, not detailing everything, but at least the first level of implementation that you will do. It's called an architecture phase. So this is the output documentation of that architecture phase. We should come before the development, but people identify it with waterfall development and agile people, consultants, etc. don't like architecture phases that much.
So interfaces are here as well?
So interfaces would be sorry, identified here. as something like very similar to classes, because they actually tell you properties and methods for classes. So interfaces are basically implemented like this. This is not an interface, this is a parent class, but it could just as well be an interface. And if this arrow was filled, if this arrowhead were filled, it would mean that this class is implementing that interface. So the idea is, if you don't have these things, it's again very complex. If you have these things on top of a very complex system, at least this helps you reduce the complexity. And the idea is you can use design patterns, that's for sure, in your code, but you can also make use of these documents and architecture phases to reduce complexity. Design patterns is not an end, it's a means to reduce complexity. The end goal is always tackling complexity, and it comes in different shapes, different methodologies, different approaches, and UML diagrams is a very, very easy way of doing this. Normally at work we do this. This is not our graph, I just found it on the internet. But normally at work we have an architecture phase, and before we start development we do this graph, and as we're developing we're improving it. So as you create new steps between, I don't know, like 3 and 4, because at that point you realize that there should be 5 more steps in between these things, then you go back to this document and update it. The biggest problems with these things is these are documented and put on a wiki, but they are stale. Nobody goes back to update them. So they write more code, they increase the complexity, they introduce new methods and functions and new classes and new interactions and steps, but they don't come back and update the architecture document, which basically renders this document useless, because now this becomes the complexity. Because you hold this as a reference, you look back at the implementation, but it's completely different. So this is a best practice of engineering. If you take the time to go back and update these documents, then it will be super easy for anybody to pick up that code, that line of code. And remember when I told you this is a human problem. The average tenure of software engineers in startups is 11 months. After 11 months, software engineers leave a company, which means you have to replace them. You have to replace that position, which means the new hire that you make comes in and has to learn all the code and all the stuff and be productive. And you expect them to not make mistakes.
Is there any way to automate how you create this and update UML?
There are certain software that transforms your classes into this thing, or this thing into classes. I actually have a project on GitHub for this. You give the UML diagram, it generates classes in PHP and JavaScript for you.
Model-driven.
Yeah. So you draw the model and then it generates some code for you. But then, of course, it can do that only once. You go and modify the code, you have to update this diagram. And people don't do that. But it means money lost, time lost, and a lot of frustration, both on the new team member and the old team members who have to teach the newcomer. So these things are therefore really also important to reduce complexity. Finally, we get to the topic of design patterns. I hope by now you understand that the goal is not design patterns. It's just a simple tool. There are hundreds of design patterns for every language or for general purpose. I will give you some books, some recommendations to read both on JavaScript and for general software engineering design patterns. But again, these things are stuff that you will identify as you move on in your career. And unfortunately, although the name is a pattern, it's not something that is intuitive. It's not something you take and say, oh, hey, I totally know what I'm going to use. I'm going to use this pattern and that one, and they'll combine and make this huge software. This is the ideal, but let me tell you, it doesn't happen. We just have an idea, an intuition, a feeling of which patterns could be used, but it's hard to identify them. It's hard to make use of them. There are three categories of design patterns. The first one is the creational, the second one is the structural, and the third one is the behavioral. Creational design patterns deal with the creation of objects. Remember when I told you about dependency injection? It's a method for object creation because it saves the car from creating its own driver. Like the car doesn't need to create its own driver, right? The driver was coming from outside. So that's a problem of object creation, and creational design patterns are tackling that, basically. The second one is structural design patterns. These involve multiple classes and their interactions. As I told you, for example, the flying ability of a bird is very problematic. Like there are multiple classes, the bird class, the chicken class, and like other bird types, eagle, whatever. They have very diverse characteristics, but they are somewhat related structurally. Structural design patterns help you identify pain points and solve them, and solve the code complexity of different classes interacting with each other. And then there are behavioral design patterns, and these are about the operations of individual classes and the actual business logic implementation. So if you have, for example, a checkout mechanism on Amazon, you buy something, you click the checkout button, you expect something to happen, right? You expect that the money will be deducted from your bank account. There will be some inventory dedicated to you. The shipping and handling companies will be alerted about your order. There's an invoice. There's an email that you need to receive, right? This is a huge business logic happening in a single click. And behavioral design patterns are there to solve problems that occur during these business logic implementations, these behaviors, and how single classes operate. So some creational patterns. The first pattern is called a singleton. It's the most simple one, and here is roughly how you would do that in JavaScript. This is a very simple person class. The idea of a singleton is, as you recognize by the name, you should have a single instance of a class. Now, I gave the example with a person, but obviously we have multiple people, so we have multiple instances, right? But think of the government. You don't have multiple governments. In a country, you usually have one government. And you don't want anybody to mess with that government. There's no way to change that government, to create a new one. Whenever you need a government in a country, you should always get the reference of the current government that has been set there by another process. Remember, this is about object creation. So the idea of the singleton is there are certain cases that you need a class to be instantiated only once. Like a second copy would bring trouble. Like a second driver who is trying to drive the car to a different location. Or like copying people.
What is if it's hybrid, so like driver and autopilot?
Sorry?
So how you define the class, like if there is a driver and autopilot, there are two things, so there are the two options. And how we behave with the singleton?
So you wouldn't have singleton for those cases, I guess. It's more like stuff that has to exist only once. Like, think about the databases. The database code that we had in our projects in the first class, it was a singleton, basically. It was a single module. Like, there is a single database that you load from the file or from a MongoDB, but there's only one instance that is representing it. There is no second database. So you're writing to one, you're reading from one, and if there were a second database, then how do you make sure you write to the correct one? Or how do you make sure that nobody writes to the other one and there is data discrepancy? You know, different databases having different data. So the singleton pattern implemented like this, you know, you keep something called an instance property on the class, And whenever somebody is trying to create a new person, as in this example, we are trying to create two different people, John and John 2. And although we think that's the case, we can create two different people, we don't. And we ensure that by checking if we have created an instance before, and if we had an instance before, if we had an instance before, we return that instance automatically. And if this is the first time this class is being instantiated, then we create that instance and save it for later use. So that when you try to instantiate it a second time, we make use of the first one and we return the first one. This is also used in, in constructs that are really expensive to create. So maybe you want to control the creation. Maybe you want to say, okay, this takes 30 seconds to initialize. I don't want you to do it 100 times during this business logic. I will make sure there will be a single instance so that I save some creation time.
Because some people claim that Singleton is the kind of anti-pattern. I mean, for me, it still makes sense to do it when you have to instance one database object, something like this.
Yeah.
What's your opinion on this?
It's basically not a anti-pattern in JavaScript. We use it all the time. For example, the very modules that we use in JavaScript, they are singletons. Every module that you require is required or instantiated only once. So it's embedded in Node.js. When you require this database connection, you know that it will be required only once. Even if you require it a second time, you know that it won't be instantiated again. This would break a lot of stuff actually, if this led to the second instantiation. So it's embedded in Node.js and in basically almost any language, but you don't just recognize it. I don't agree that it's an anti-pattern, but that's a further philosophical discussion. So the next one is the factory. This is a very simple implementation. Like, you want a car, okay? You want to buy a car. Do you want to define the engine of the car? Or do you want to define the maximum speed or the price of the car every time you want to buy a car? No, you just know what model you want to buy, right? And this is what your usage would look like. You say, hey, BMW factory, give me an X5. Or hey, BMW factory, give me an X6. I don't care how you create it. I don't know when you created it. Maybe you're giving me something from the inventory, or maybe you're building it as I want from you. I don't know about those things. I don't want to deal with instantiating my own car instance, passing in my own engine and my own seats. I just expect a car from you. So you create a factory, you instantiate a factory, and you tell the factory to give you instances, and you define the properties. You define the model, for example. And what it does is, it checks it, and if it's an X5, for example, it gives you a slightly less expensive car, and if it's an X6, it gives you a slightly more expensive car with a better top speed. But the factory actually decides the instantiation of the objects. It knows when to create them. Maybe further down the road there would be some inventory logic implemented here. Maybe there are some cars it created before, and it will just give you whatever is available, whatever suits you. And if it cannot find it in its inventory, it will create a new one for you. This is basically how cache mechanisms work. Like when you implement a cache in your backend code or front-end code or whatever, that's an inventory of items. You say that if this is the first time you're creating that cache, instantiate it, create a new one, and give it to me. And then, if it's the second time, just serve me from the cache so that I save a very lengthy, costly operation. Structural patterns. The first one that I like most is the compost pattern. This is where the building blocks, the Lego building blocks come in. And the idea is you have certain software like a tree that repeats itself and that builds similar structures. Like a tree has a trunk, right? It has some branches. If you break the branch, it looks like a trunk. Or branches go on to have further branches down the road, and every branch can have multiple branches, or at the end they have some leaves, right? A leaf doesn't have a branch. It's a unique thing, but anything between the trunk and that leaf is basically repeating itself. So there are certain patterns that we use, or certain use cases that we need the compost pattern. The first example that comes to mind from front-end engineering is the DOM. It's even called a tree, DOM tree, if you know the word. The case is basically every DOM element is like a branch. They can have multiple DOM elements in them and more. And then when you go to the end, you can find the leaf, which is still a DOM element, so it's still a composite, which can contain multiple versions of itself or other instances of the same type. So a DOM tree is the perfect example for the compost pattern implementation. But here is another example. So we have something called an equipment, okay? Look at the method names. It has a get price. So there is a certain equipment and you can fetch its price. Also it has a name and you can set and get its name basically. So we have something called a composite that extends from this equipment, and it holds an array of equipments, much like the DOM tree or like a branch. It can have multiple branches, right? It holds an array of equipments basically. You can add new equipments to it, and of course you can still get the price because that's an equipment, right? It has to have this get price method. How do you calculate the price of a composite equipment? Raise your hand and tell me. How do you calculate the price of a composite equipment that has multiple equipments?
You add all the prices of all
Yeah. Yeah, that's basically as simple as that. And this is what we do here. For every equipment, we get their prices. And we basically add them up. This is called a map and a reduce operation. It's very powerful, functional JavaScript. And we make use of this all the time. But the idea is we get the prices of each equipment and add them up to find our own price. What would happen if a composite would include another composite? You know, a composite that includes 5 more composites. Can it do that? It can do that, right? Because the add method expects an equipment, and a composite is an equipment. Do you see where the solid patterns come into practice? The Liskov substitution principle, which stated that a child class should have all the properties of its parent class and can pass in as a parent class. So the composite expects an equipment. A composite is an equipment, is a child class, and it has all the properties of the parent class equipment. So it can actually pass in as an equipment, which means you can have a parent composite and multiple child composites under that. Does this make sense? So here is some other examples of equipment. A cabinet is an example of a composite which can hold multiple objects, and then we have some leaves. They are not composites themselves. A floppy disk, a hard drive, and a memory, they have different prices, they have different names, okay? And then what you can do is you can create a cabinet, and you can add these items to the cabinet, and still you can get its price. And it will give you the total price of these items. Now, you could create a second cabinet and put this cabinet in the second one, and I don't know, put a cabinet that's full of equipment for like $500 again, and the end result would be 1,100, right? Because you still add them together. So it's like basically it's like an infinitely growing tree of items that can involve each other, and it's very useful. I mean, it's always in the browsers. It's our lives basically.
Can you just mention how the recursion works in the previous slide?
Here?
Yeah.
Yeah.
When we get price.
So the thing is, again, let's say you have one composite, like a cabinet, and you have another cabinet, and since a cabinet is an equipment, you can add it. You can add the second one to the first one. And what would happen then, if you want to get the price of the first one, is you call the get price on the first instance. Now it has a single item in its equipments, and it's another composite. But what it does is, if you see here, it goes and fetches the price of that composite. So, and it's implemented here.
No, that's fine. With
Yeah.
just one equipment. But what if the equipment is an array? So like another composite.
So that's okay, because see, this is a composite and it has a get price method. It will keep calling this method and it will go into the array of items until it finds a solo equipment that doesn't have an array, that returns a number.
Because I was expecting something kind of a loop, and at the beginning we don't know how many equipments a composite includes. And
Exactly. That is the point of this design pattern. You don't care if this is a leaf, like an equipment, this is a leaf, or if it's an array, like a composite. You don't care. You just have an equipment list. All you care is they have a method called getPrice. As long as the equipment that you have, whether it's a composite, a cabinet, or an equipment, as long as it has a method called getPrice, you can recurse into it. So a cabinet has a method getPrice. It holds another cabinet that also has a method called getPrice. It can hold another cabinet that also has a method getPrice. And it can hold a floppy drive that has a getPrice method that returns a number. And that is when the recursion ends. Basically, you go back and add up all the records, all the numbers.
Basically, there is a loop which is done by the back function.
yeah, now
Because
I
the
see.
equipment's
It
mapped.
makes it tricky.
By the way, your get price could be more simple. isn't it? If you add the price of equipment A plus price of equipment B, you can remove the map function.
But map function doesn't give you the individual equipments. It gives you just one equipment out of the array and one at a time. So
In this equipment, and then you reduce, and you return get price.
you could definitely use only a reduce here, and you could do a.getPrice plus b.getPrice. Yes, you could remove the map, but it would both work. Yeah.
So do I understand rightly that get price is the leaf here in the tree?
No, the leaf is the equipment.
Leaf is the equipment.
Get price is just a property of the equipment. And again, get price is also reflected in the composite, so that you can start from the absolute bottom and go and make your way up to the leaf by summing up all the get prices.
And I'm sure that you will be providing us the presentation.
Yeah.
On the slide. Thank you.
Okay. The other one is the decorator. Let's talk a little bit about the name. What do you understand from the name decorator? What does it mean to decorate something? Raise your hand. Yeah.
To stylize it.
To stylize it. What exactly?
What do you mean, what exactly?
That's the point. What would you stylize? Something.
Object.
Yeah, an object that's already in your hand, right? But you don't like some properties of it, and you want to modify them after it's been created, right? That is the point about the decorator pattern. It's remember, these are structural patterns. These are not creational patterns anymore. So we have here a class called pasta. Okay, it has a price again, and a version of it called penne, and it has a certain price. The default pasta is basically free for all. That's amazing. That would be amazing. I could have it every day. But if you want a penne, you have to pay 8 euros. Now, you have something called a pasta decorator. All right, it accepts a pasta and saves it as a property. See, it doesn't create the pasta because this is not a factory. This is a decorator. This takes in an existing pasta, saves it for decorating it later, and it can give you the price of that pasta. All right, and you can add sauce and cheese as extras to our pasta. This is actually how this thing is implemented in real life in shops, like when you add, sauces or cheese or I don't know, sausages or jalapenos, whatever, to your food. This is how it's actually done, or how it should be done. I'm sure some people don't do that. But you have a sauce decorator, and again, it takes in a pasta. And when you ask the price of it, since it added the sauce on top, it requires you to pay 5 more euros. So it modifies the price. It gives you the price of the parent class, so whatever it would pass, and adds 5 euros on top. And if you want cheese on your pasta, it's like you have to pay 3 more euros. So the idea is you have a bare object, you have some decorators that add certain additional features, additional functionality, and they can also modify modify the existing behavior. So they can also modify the price. Let's see how we use that. So you create a penne. Okay, this is the bare bones object that you have at hand. And then you basically have a new sauce decorator, and you pass in the previous penne that you created, which costed 8 euros back then. And basically this gives you a penne with sauce. So now you have a sauce on top, and when you use penne with sauce.getPrice, you'll be billed 13 euros. And what happens if you want to add cheese on top? Well, you get a new instance. You get a new penne with sauce with cheese, basically. So you can pass in the result of a certain decorator to another decorator. Basically, you can chain these. You can have multiple decorators that are acting on one another. And you see the price is increasing like crazy. I thought I could have it for free.
Can you go one slide back, please?
Yes.
Because I'm wondering why you have to have the get price function on top of the pasta decorator.
Because you see, the pasta decorator actually extends the pasta class.
Yes.
So a pasta decorator is actually a pasta.
Exactly. So in that case, why do they need to rewrite a get price method? Because get price is just doing the same what pasta is doing. It's returning the price. Or maybe I missed something. I don't know.
So the idea here is the penne that you created was an instance that we keep in memory here in this thing as a property, but we don't directly modify that. So basically, we don't create a pasta decorator from scratch and nothing else. If you look at the example, we have an existing penne already. And we have a pasta like source decorator is a pasta decorator. So we pass in an existing instance of a penne.
Okay, so we're doing a copy of it's not the same penne we put into.
Yes. I mean, the same penne that we put in is still living here, is as in this.pasta, but basically at the end, what we get is penne with sauce and cheese. This is something else. This doesn't have. This just holds a reference to the original one, but this is a different instance.
Okay, so when we would not add the get price method in the source decorator, we would modify the original
Yes.
that we put in. That's the reason
Yeah.
I have. Okay, got it.
If we go one forward, so then if we replace penne with pasta, and at the last instance, penne with so pasta with sauce and cheese get price, what it could be? So like it could be just 8.
Yeah.
Yeah.
And the idea is, again, remember Liskov substitution principle. This is okay because child classes still function as the parent class, right? So our code always expects pasta. All the code that we have expects pasta. Like the sauce decorator expects a pasta, the cheese decorator expects a pasta. You can pass in either a pasta or any child class of it, like the pasta decorator. So you see the order here, penne with sauce and penne with sauce and cheese. What would happen if the order were reversed? So we still have a penne, but first we get a penne with cheese as an instance, and then we give that to the sauce decorator to get a penne with cheese and sauce. I mean, it's still technically the same. The price would be the same, right? And we just expect it to work. That is how you make it work. If always you depend on the pasta, then you can say, okay, the sauce decorator goes first, and the pasta and the cheese decorator goes second, or vice versa, and it doesn't matter, it would work. So you could have, if you were a bad software designer, you could say a sauce decorator can only operate on cheese decorator, okay? Then that would mean that you have to first create the cheese version. You can never have the sauce version because you first need the pasta decorated with cheese in order to put sauce on top. That would be a very bad design.
That means like even if the decorator is there, the composite is working.
The what?
So like here is the combination. So even if
Yeah.
you have here the decorators, but it is based on the composite. Is it the composite pattern too?
So this is not exactly a compost pattern, but they of course share a similarity basically. I mean, it's extending the class, having the same pattern of having the same function. But the composite pattern doesn't keep the previous one as an instance member. So there is only a single instance in the composite pattern of items, but here the penne with sauce is a different instance than a penne. And the penne is basically, it still lives there at its heart, at its core. So there are some differences, some structural fundamental differences, but of course it's a very similar pattern.
But then in this case, you could just have penne with cheese, for instance, because it doesn't accept it.
Currently, you can have it.
Here, but on the other one, you only have cheese decorator added to penne with sauce and cheese, so you don't have one without cheese, without sauce here.
In this current example, yes, but that was not the goal. If I wanted to have penne with cheese, I would say const penne with cheese equals new cheese decorator in parentheses penne. That would, like, I give it a raw penne and it gives me back to me a penne with cheese on top. And the price would be like, what, 11 euros? So this pattern allows you to do that. Does it make sense? Yeah. let's speak about the behavioral patterns. The first one that comes to mind, the one that I love most, is the strategy pattern. And it's mostly used in situations where you have multiple ways of solving a problem or solving a part of the problem, and you basically want to make sure you have the flexibility to change the way you solve the problem. So you have a problem definition, you have a solution definition, multiple of them, and at runtime, at any given time, you want to be you want to have the flexibility to use any of the solutions with the main problem. So the main problem cares about the solution, but then you can add more and more and more solutions. Let's see an example here. I'll first start with the implementation. So we have a shopping cart item in our e-commerce platform, in our e-store, okay? And the idea is we have certain discounts for certain people, certain user types. The default is a guest account, so there are no discounts. If you have items worth of 100 euros, you are requested to pay 100 euros at checkout. Then if you are a regular customer that is registered with us, we have a 10% discount for you. So if you spend, if you want to buy items worth of 100 euros, you pay only 90. And then if you have, if you're a premium user, maybe you pay us a monthly fee or something, fixed fee, then we increase our discount, and you have 20% discount for the items. And if you buy items worth of 100 euros, you pay only 80. So here, the shopping cart doesn't want to deal with the discount calculation. If you remember the single responsibility principle, it's not the responsibility of the shopping cart to identify the discounts based on different user types and to make the discount. It just has a notion that discounts will be there and will be applied, but it just doesn't care how that is calculated. It defers the calculation of discounts to stuff called strategies, okay? And you have a strategy for the guest to calculate its price, a strategy for the regular users, and a strategy for the premium users. And let's look at how it's implemented. So the shopping cart expects something called a discount strategy, and it saves this as a member variable, okay? And initially, of course, it has zero euros because you didn't buy anything yet. So it has a set amount method, which we would call after we add items to your shopping cart, and it updates the amount. And this is how we implement the strategies. Guest strategy returns the amount, there is no discount. Regular strategy multiplies it with 0.9 so that there's a 10% discount. Premium strategy multiplies it with 0.8 to give you a 20% discount. How does the shopping cart make use of this? When you call the checkout, remember it had saved the discount strategy as a member variable here in the first line. It basically makes a call to that function. That discount is a function, a strategy is a function, could be a function, could be a class, doesn't matter. In this case it's a function. So it calls that and it says, hey, this is my original amount, okay? My original amount is 100 euros. Do whatever you want with this and return me the result. So the actual solution is deferred to individual strategies, which means in the future you can have many more strategies here. You can have 20 different cases, you can have referrals, you can have coupons and stuff. The shopping cart wouldn't change, right? As far as it's concerned, the shopping cart implementation is done. But you can add more strategies to expand the features of your application. So this is how you solve, again, complexity. if you want to add referrals, if you want to add coupons and stuff, you don't need to change the shopping cart logic at all. You just implement a new strategy, and as far as the shopping cart is concerned, it just works. So it's a very, very powerful pattern, the strategy pattern. For example, this is the topic of next week, authentication, but you see some web pages give you multiple options to sign up or log in. You can sign up via email, or you can use Facebook to create an account in certain websites, or you could use Twitter or Google+, whatever. So you can use your existing Google account to sign into other applications, right? All of these are implemented as strategies, as login strategies. So you can, basically you define what that strategy has to do. It has to take your account credentials and log you in at the original website and redirect you back to the application that you want to log in. It has the definition of the problem, and then the solutions are varied. You could have 10 different websites trying to log you in. You could even log in with your GitHub account. You could log in with your LinkedIn account. There are just different strategies, but the problem of logging in is the same, and it doesn't change. It doesn't care how many or how different strategies for login that you have. And this is basically what we're going to build next week in the class. But yeah, the library that we're going to use has like 300 different login strategies for your web page. So you're free to choose from any one of them. And it's very, very simple to use thanks to this pattern. The strategies they have a very nice interface, very clean interface, very easy to implement, and they are atomic units.
Is using like two-factor authentication, for example, another strategy for login?
Sure, could be, yeah.
If we didn't know about this, we would just use like a very long if else.
Exactly. Then every time you want to implement a new strategy, you would modify the shopping cart and put an if statement there. Or if this guy is account type this, make use of this discount. Or if this guy is account type this, make this a discount. It would be horrible. It would actually break the open-close principle. Because you're not adding new methods or new properties, but you're modifying the existing implementation, the existing feature. You're modifying checkout every time you try to expand your software, which is an additional complexity. But if you have multiple strategies, then basically there is no complexity at all, because it's basically you're repeating the same thing. It's a function. Create another function, you're done. You see that it's a strategy, you don't even have to think about it anymore. You know that it goes into the checkout. The checkout doesn't care about how many or what kind of strategies you have. It's very, very simple. And the last one I'm going to talk about today is the observer pattern. This is, again, arguably one of the most used design patterns in the world, and especially in JavaScript, and is very close to event-driven programming. So, whenever you click a button or the web page, there are certain events that are firing, like a click event fires, and you can get notified of this thing, right? You're doing an action based on that click. You can show or hide a certain element on the page, you can change some colors, you can submit a form, basically anything that you're doing, or like you can check out, right? So the observer pattern is basically built for these kind of scenarios. There are certain events happening in the system. There are certain behavior changes or state changes of some objects that have been created before, like a web page, and we want to be notified of those changes. So, for example, when there's a shopping cart, we wish to be notified when the shopping cart is submitted and the order is submitted, because, for example, we will implement analytics on top. So we will track how many people click on the shopping cart button or the submit button. So this is an event, and we want to observe that. I'm not going to show you any code for the observer pattern. This is like a very small homework for this lecture, if you wish to do that, of course. I expect you to come up with an example observer implementation in JavaScript, and I'm going to talk a little bit more about how you could implement that. So the idea is, just like the strategy pattern, keep in mind there is a certain class like the shopping cart, okay? And we don't want to touch it. We just want to expand the functionality of our program, but we don't want to put more complexity in the shopping cart. So we want to be notified whenever somebody is changing the amount of the shopping cart. Like they are adding a new product to the cart, right? That's what it means to change the amount. I want to track those in Google Analytics, and therefore I need to be notified of the amount changes. So how could you do that? How could you implement that? Callbacks? Yeah? That would be hard coding it.
I would put an attribute to the shopping cart, a global attribute, and every time when the set amount or checkout, whatever you want to control, I would put something like a counter. Every time the function is called and the counter sums up 1, and then at the end we're going to know how many times the functions was called.
So what if you want to repeat this for another class that's not a shopping cart? You would do the same thing there, right? This is actually the definition of repeating yourself. There is this certain complexity of counting how many times we click on this thing and that we want to track it. But this is a custom solution that we are copying and pasting, a custom structure that we're copying and pasting in other classes, and we're repeating it. So it's a way to solve this problem, but it's not a design pattern because it's not obvious at first sight for why you're counting that. And you see that counting logic in every single class that you implement this. So can there be a way to abstract this away so the shopping cart doesn't care about this at all?
Notify function. Yeah,
Exactly.
Create some kind of interface, a decorator, so whenever a service, Google Analytics or something else, would like to be notified, this class has to implement this interface.
What does that interface have? What does that interface have?
One method like be notified.
Exactly.
And our shopping cart or whatever should have some kind of list and an add method. So whenever service would like to be notified, I add this kind of service, and the shopping cart doesn't care what kind of is because it implements the interface, so it knows there's this one specific method I have to call when the amount changes.
Yes, exactly. So the idea is, of course, to have an interface, but the idea is the shopping cart is an event generator. It can notify other interested parties that are observing the shopping cart. So that's why the name observer. The Google Analytics class would be an observer, and you could pass in any observable to the observer. So it could be a shopping cart, it could be another logic, and the only change that you do here in the shopping cart would be to notify the observers. So you identify set amount as an important property, as an important function, and you want to be notified when it's called. So what you do is you keep a list of observers here in the shopping cart, and whenever you call set amount, you go over the list of observers and you're notifying them. You don't count the numbers here. You just notify the external observer and say, hey, you are interested in this set amount thing, do whatever you want with it now, like because it happened. And this gives you the ability to have multiple observers. To maybe, you would count it one by one, another observer would count it in multiples of 2 or 3, whatever. Or you could have an error handler to check for the imbalance of between the amounts and the discounts, or if there are any errors happening in this call. So the idea is shopping cart shouldn't care about that functionality at all, but it just notifies the world, anybody who's interested in the shopping cart, that an event of interest has happened. It's where the observer pattern comes in handy. It's like a strategy pattern again, and it makes you sure that you can have multiple observers operating or observing a single item and still doing different logic. You could have a logger to log the incoming set amount calls, for example.
So whenever we want to put a new observer, then we have to change the function.
Not this one. You create a new observer, but since you're operating on an interface, all the observer has to have is a notify method. So as long as you have an observer that has a notify method, the shopping cart can function on that. So of course at runtime the list of the observers in the shopping cart grows, but we're talking about the code complexity when we're developing it, which means you don't need to change the shopping cart. Once it's an observable, you don't need to further change it to accommodate more observers. Again, one observer will be Google Analytics to log the amount, to get the amount of clicks, the number of clicks in set amount. The other one would be a log to see if there are any errors or the amount. And you don't need to change the shopping cart implementation in code to get this, basically.
So these guys you will be putting in the interface.
So these will be individually different classes implementing that interface of one single method, notify. So the Google Analytics observer has a notify method, the logger error handler has a notify method, and basically somewhere else in the code you say, you instantiate your shopping cart, you say, hey, this is my shopping cart, you instantiate the observer, like Google Analytics observer, and you say, hey, Google Analytics observer, go and observe this shopping cart. What it does is it registers itself with shopping cart, and then shopping cart notifies whatever the list of observers whenever there's an event of interest. So it doesn't go into interface. You have a single interface that doesn't change, that's a notify method, and you have a single implementation in shopping cart as an observable. Then, much like strategy, you can have 100 different observers, but you don't need to change neither the interface nor the shopping cart class.
That means we can play with the constant amount and shopping cart observers and modify everything.
Modify everything.
Modify whatever we want.
Observables don't usually modify anything. They are just to observe. They just watch what happens, and it's basically actually a bad practice if the observer changes the observable, because it could trigger a chain reaction, because you have to notify everybody again of the change. And what if someone else changes that actual observable again? There's another round. You can have an infinite loop there, basically.
That means changing is the function strategy.
So yeah, if you want to change it, you use the strategy. If you want to observe it, basically you use an observer pattern.
Can you show the place where you created shopping cart again?
This one? Or, oh yeah, this one.
Because there's something I find a bit weird, is that you have these discounts, which are happening, and in your shopping cart class you have a discount property, which is never set it.
No, you set it in the constructor.
Just leaving the discount is the strategy.
Yeah, the discount is the strategy. You pass in the strategy function.
There is a strategy, but is a function of amount.
Yeah, of course. It takes in an amount, and this is how you instantiate, or how you call this.
Shouldn't strategy return just a discount?
Sorry?
Shouldn't strategy shouldn't the strategy function just return the discount, like 1 or 0.9 or 0.8?
So if you did that, you would put the discount functionality or responsibility in the shopping cart, right? Like the multiplication should have happened in the shopping cart. What happens if you need to add taxes? You would still modify the shopping cart. That's not the responsibility of the shopping cart, actually. So the logic, the actual logic, goes into the strategy. That's why it's called a strategy.
Okay, so discount is actually a function.
Yeah, discount is a function. Because you could have, you could have this multiplier here, or you could have a different, a coupon that gives you 10 euro constant discount. So not a percentage, but
Yeah, so maybe the name discount is misleading. Name of the property.
why? It's a discount.
Yeah, it's more compute checkout also.
While naming is hard, it's one of the hardest things in computer science. But I would say discount would work because we could have another strategy for taxes, and this could read like this.tax in parentheses, this.discount in parentheses, this amount. So it's not, this is not computing the checkout. This is, the strategies are only computing the discount amount. You could have a different, you would have to have a different strategy for taxes or for other calculations. Like group discounts for, I don't know. You were saying?
Yeah, I'm not sure I understand completely how the observables part works. But I'm just wondering how is adding that not giving the checkout cart an additional thing to do. You know how you're saying that you have to give just one function, or not one function, but one task to per item. And I was just wondering, isn't that a little bit giving it extra things to do?
You could argue that. That's why there's a whole branch of programming called aspect-oriented programming. You should read on that. They basically say what you say, and they say for these things we shouldn't modify the existing structures. So it comes in meta-programming and aspect-oriented programming. But it wouldn't be, in my opinion, because it would be changing the shopping cart. It's like it's implementing a new interface, that's all. That's also another implementation. That's also another way to do that. Some people implement event managers in these things. So instead of changing the shopping cart implementation to be an observable, they have an observable element in them as a property. So it's like this dot event emitter equals new event emitter or something. And whenever there's a, for example, there's an event to be tracked, like set amount, they do this nokta event emitter dot emit, and that's where the observers listen. So there are different ways to implement this pattern, but observer is the simplest version, the first version that came to people's minds, and it's also good for learning purposes. So I encourage you to read more about it and to implement it, basically. But fundamentally, no, because it's converting shopping cart into an observable, which is a very, very fundamental function. So it's not like a bird gets arms or something, or I don't know, a cat starts walking upright. It's like, it's a cat that you can see. So like beforehand all the cats were invisible, and now you can see them. So it's like at that level of structure fundamentally. So it's not giving it as an additional responsibility, because it's not business logic related. It's a behavior. It's a behavior that we're adding. But yeah, so the references that you have to at least read the introduction chapters. Design patterns. Elements of reusable object-oriented software. These are names of the books. Patterns of enterprise application architecture. This is the thing that created the name design patterns. It's also known as Gang of Four, because four great software engineers wrote it. Then you have Clean Code and Clean Architecture, amazing books if you want to learn more about architecture. You have Pro JavaScript Design Patterns, which gives you the implementations of most of these patterns in JavaScript with really great examples. Unfortunately, it's for the front end. The book is like 10 years old, but it's still a super solid book that I always use in my studies and in my classes. And then there's Code Complete, which is a little bit heavy. So it's like, I don't know, like 600 pages or something. But again, it's like these are timeless books. These are books from 90s. And they still define how software engineering should be done like. And you'd be amazed, like 25 years after, we still don't get these right. We still fail to implement these. That's why there's so much pain in software engineering. But that's mostly it. So the examples that I used in the design patterns portion is from this repository. The slides are available there, and this is my Twitter handle, minus the Twitter bird that can't fly.
Why is it so that these papers are not being implemented? They forget about it, or they just was they learned?
If they only knew, they don't even know about it.
They learned about it.
Like, ask your friends at work how many people read through these books, or how many of them. Like, okay, this is a very very small book, but the others are giants basically. So leave this out, do a survey, how many people read these books. You have to read them over and over again to understand their value, because as you advance in your career, the books change their meanings. When you read it again, you understand you look at it with a different understanding and different insights with your different experience. So it's like you have to read them like every couple of years. And basically people don't read. That's the biggest problem of our age. People don't read. If they read it, software would be better. We wouldn't suffer. But it's very simple. Like, you read these, you apply those things, and then you're immediately a better software engineer. It's like upgrading your career, like a decorator pattern. You're upgrading yourself with new skills. So it's a lot easier, actually. You invest a couple of weeks to read one of the books, and then you're eternally a better software engineer.
Could you just put it on the slide so we can go to the URL?
This one? Yeah. I mean, I'm gonna share this over Slack. So join our Slack group, Women TechMakers Berlin, and this will be there. The presentation and the recording, hopefully.